everyone, myself Dr. P. Ashok Babu, working as Professor and Head EC Department. So in this video, I'm going to discuss about some important problems on transmission lines too. So first one is a transmission line of length 0.4 lambda has a characteristic impedance of 100 and is terminated by a load impedance of 200 plus J into 180 ohms. So by using Smith chart, we need to find out the voltage reflection coefficient VSWR input impedance of a line. So here for this, first in transmission lines, we need to find out the normalized impedance value. From normalized impedance value, draw a circle in Smith chart. So in Smith chart, so here the circle will be like this. So here the Smith chart will touch the x-axis at this particular point. So this is nothing but the voltage standing wave ratio. And from this, we can find out the reflection coefficient. So from the center of the Smith chart, extended line, then we can, from this, we can find out the reflection coefficient, and then we can find out the input impedance of a line. So calculate the characteristic impedance of a quarter wave transformer if a 120 ohm load is to be matched to 75 ohm line. So this also can be, we can calculate the characteristic impedance by using the Smith chart. Draw a Smith chart. From the Smith chart, we can find out the characteristic impedance. So here a transmission line having 50 ohm impedance is terminated in a load of ZL is equal to 40 plus J30 ohm. Describe the voltage standing wave ratio. So here we can find out the voltage standing wave ratio. To find out the voltage standing wave ratio, so VSWR equal to, we have 1 plus mod K by 1 minus mod K, where K is the reflection coefficient. First find the reflection coefficient value. Reflection coefficient equal to, here we have ZL minus Z0 by ZL plus Z0. So from this find out the reflection coefficient. Then if you substitute the reflection coefficient in VSWR, you can find out the voltage standing wave ratio. A lossless line having an air dielectric has a characteristic impedance of 400 ohms. The line is operating at 200 megahertz and Zn equal to 200 minus J into 200 ohms. Use the Smith chart, find the standing wave ratio ZL, and we need to find out the distance from the load to the nearest voltage maximum. So again, you draw the Smith chart. First find out the normalized impedance. Normalized impedance equal to ZL by Z0. So from this we can draw a circle, and from that we can find out the VSWR and load impedances. A lossless transmission line with Z0 equal to 50 ohms is 30 meters long and operates at 2 megahertz. The line is terminated with a load ZL equal to 60 plus J40 ohms. If U equal to velocity equal to 0.6 C of the line, then find the reflection coefficient, standing wave ratio, and input impedance. So here we can also find the reflection coefficient. First we can find out the reflection coefficient K. So K is equal to here ZL minus Z0 by ZL plus Z0, and VSWR equal to, it is 1 plus mod K by 1 minus mod K. Then we can find out the input impedance. So in this we can find out the reflection coefficient VSWR and input impedance of a given transmission line. A 100 kilometers long transmission line is terminated by a resistance of 200 ohms. It has the following constants: Z0 is given, alpha is given, beta is given. Find the reflection coefficient and the input impedance. So here we need to find out the so P is given. So characteristic impedance is given and P is given. So here we have P is equal to alpha plus J beta. P is equal to alpha plus J beta. So here we have the input R plus J omega L, which is equal to R plus J omega L equal to, we have Z0 into P, Z0 into P. So from this we can find out the input impedance. Then we have the formula, reflection coefficient K is equal to ZL minus Z0 by ZL plus Z0. From this we can find out the reflection coefficient and input impedance. A low loss line with Z0 equal to 100 ohms is terminates an impedance ZR. ZR equal to 115 minus J into 60 ohm. So the wavelength of transmission line is 3.5 meters. Using the given Smith chart, we need to find out the VSWR. So here Z0 is given, ZR is given. So Z0 and ZR, then we'll find out the normalized impedance. The normalized impedance equal to ZR by Z0, ZR by Z0. So from this, draw a circle. So here the circle which touches the x-axis at a particular point. That particular point is known as the VSWR from the Smith chart. So in this way, we can find out the voltage standing wave ratio, reflection coefficient, or voltage maximum or voltage minimum from the Smith chart. Some important derivations in transmission lines 2 are: explain the significance and utility of different lengths of lines, lambda by 8 line, lambda by 4 line, and lambda by 2 line. Explain the significance on the design of single stop matching. So here we can design the single stop matching and double stop matching. So explain with the needed sketches how the input impedance of a lossless line varies with the frequency. Next, derive the expression for input impedance of an uniform transmission line which is terminated with a load ZL. And so we need to discuss the properties of a quarter wave length transmission line. Then explain the significance of what is the significance of V maximum and V minimum positions in a Smith chart. So hence derive an expression for impedances of these two, V maximum and V minimum. Next one, explain the method of determining the input impedance of a line using Smith chart. So by using the Smith chart, we need to explain the different parameters. So explain the significance and design of double stop matching. So single step, we need to derive the expression for single step matching. To avoid the disadvantages, we need to derive the double step matching. So write a short notes on reflection coefficient and VSWR, voltage standing wave ratio. Next, explain the design procedure of single and double stop matchings, impedance matching. Here we need to explain the design derivations for designing of single stop matching and double stop matching. So there are the different important derivations in the module 5th or transmission lines 2. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.